Hey everybody, John Travolta here, and this pre-calculus lesson is on continuity and end behavior. Alright, it's a big lesson, you guys, so we're going to go kind of fast on here. Okay, so graph each function and its inverse. We did this in a prior two lessons, you guys, so remember that this is a linear equation, y equals mx plus b. So remember, to get the inverse, you switch the x's and y's, so then it would be x equals negative 3y plus 4, and then solve for your new y. Okay, so you're going to get this graph right here. Okay, so here's the negative 3x plus 4, and then here's the inverse graph right there. Okay, this one you're going to go x equals y squared plus 1, and then so you're going to get subtract 1 from both sides, and then you get y equals plus or minus the square root of x minus 1. Okay, and then notice this is a parabola. That's this guy right here, and it's going up there at plus 1 right there, and so here's the inverse over here. Okay, we did that in our last lesson. Okay, this is a square root one, you guys. A square root one is getting shifted to the right one and up 2. Okay, so there it is, to the right one and up 2. And I just graphed that. I guess I didn't graph the inverse of that, you guys, so I just graphed that. Sorry, I don't have the inverse on that. Okay, so continuing and end behavior. So graphs and discontinuous functions. Okay, infinite discontinuity. Okay, so this is a graph that's not continuous because they don't touch each other right here, and they're shooting up to infinity. So that's why it's called infinite discontinuity. Okay, they're not continuous. That's the discontinuous, and they're shooting up to infinity. This one's called jump discontinuity. They're not continuous because they have to jump right here from this piece to this one right here. Okay, this one right here is point discontinuous. Okay, where like a denominator would get you a denominator of 0, like this one. X can't equal negative 1, so at x equals negative 1, there's a 0 right there. I'll show you how to graph this guy a little bit later using some algebra skills and long division and stuff, but not in this lesson. We don't have time. Okay, so continuity test. A function is continuous at x equals c if it satisfies the following. The function is defined at x equals c. The function approaches the same y value when you approach x equals c from both sides, the right side and the left side. Okay, and the y value that the function approaches from each side is whatever f of c is. So I have examples that explains this, you guys. So determine whether the function is continuous at the given values. Okay, so first of all, you guys, we got to plug in 1 right here. So let's plug in 1 right here. 1 squared, 1, and then so 3 times 1 squared plus 1 minus 7. So f of 1 would be negative 3. Okay, so far so good. So now what we got to do is see, we're going to approach x equals 1 from the left and 1 from the right, and we want to see, does it equal negative 3, or does it approach negative 3 as we approach 1 from the left. So here's approaching 1 from the left, and that's how it's written right here. This says x approaches 1 from the left-hand side. So it's a positive. It's just telling me this negative says I'm approaching it from the left-hand side. So here's x equals 0.5, 0.7, 0.9. Here I'm think of a number line, and I'm approaching 1 from the left. So 0.999, and when I plug in these x values up into here, 3x squared plus x minus 7, I get these. Okay, now 0.5 is not very close to that, but I get negative 5.75. But as I approach 1, as these numbers get closer to 1, these numbers are getting close to negative 3. In fact, if I did 0.999, I bet you this would be negative 3.0000 something. Okay, so as x approaches 1 from the left, f of x is approaching negative 3. Okay, let's approach 1 from the right. Okay, think of a number line, and I'm going towards 1 on the right. X equal 1.5, 1.3, getting smaller, but it's still numbers that are to the right of that. And notice when I plug in all these numbers up here, I find that these numbers are getting closer to negative 3 also. In fact, if I did 1.001, that's closer to 1. This would be like negative 2.99 something. I don't know. Okay, so we just want to make sure, and you don't have to do all of these, you guys. You just, maybe do this one right here, see if it's approaching negative 3. Do this one right here, see if it's approaching negative 3. And if it does, then you can say, yes, it's continuous at x equals 1. Okay? I know you're thinking, why? You'll see why in a little bit. Okay, what about this one? Y equals x minus 2 over x squared minus 4, and we're going to try it at x equals 2. Okay, so plug in x equals 2, and you get 0 in the denominator, and you can't have 0 in the denominator. That means this guy is not continuous. I'm done. Okay, at x equals 2, it's not continuous. Okay, a piecewise function, you guys. So f of x, which is y equals 1 over x when x is greater than 1, or y equals x if x is less than or equal to 1. And we want to know what's it equal when x equals 1. Okay, so we're going to approach 1 from the left and from the right. Okay, so the function is defined at x equals 1 because right here, less than or equal to x equals 1, then y is going to be 1. F of 1 would be 1. Okay, so let's approach 1 from the left. Okay, 1 from the left, this is going to be this function right here. I'm only going to use this function right here. This would be from the right of 1 because it's greater than. So when x is, whatever y is, x is. So when x is 0.9, y is 0.9. When x is 0.99, y is 0.99, and so on. Whatever x is, f of x or y is. Okay, so as x approaches 1 from the left, y is approaching 1 from the y is approaching 1. Let's approach 1 from the right. Okay, so I'm using this function right here, 1 over x. So I plug in 1.1 into 1 over x. So 1 over 1.1 gets me this. 1 over 1.01 gets me this. 1 over 1.001 gets me this. Can you see it's approaching 1 from the right also? Okay, so as x approaches 1 from both sides, f of x also approaches 1. So we can say that yes, it is continuous. Now it's not saying to graph this, but that would be the graph of that guy right there. And even though they're different functions, it approaches 1 from the left over here, and it approaches 1 when I go over here. Even though they change directions, it's still approaching that little point right there, 1 right there. Okay, end behavior. End behavior is another way to study functions by describing what your y value does when your x becomes very large, when x goes to infinity and x goes to negative infinity. So when x goes to plus or minus infinity, we want to see what the heck y is doing. So if the highest degree is even, this is the shortcut, you guys, and the leading coefficient is positive, okay, the highest, like say we had 5x to the fourth, then plus 3x to the third, plus 2, something like that. My 5x to the fourth, the 4 is even. So that was if the highest degree is even, and your leading coefficient, the 5 would be my leading coefficient. If it's positive, then my end behavior is always going to be infinity. Your graph is either going to be something like this, okay, shooting up like this, or it might be a graph that looks like this. But notice it starts way up here, and over here it ends up here, like a touchdown. You know, like a referee doing a touchdown. He's got his hands going up right here and right here. Okay, so if it's an even function and it's positive, your end behavior is going to be, no matter what, it's going to be touchdown. Okay, now if it's an even and it's negative, it's just going to flip these guys upside down, so my end behavior is going to be negative. Okay, it's like an upside down touchdown. Okay, if the highest degree is odd and the leading coefficient is positive, okay, then as x goes to negative infinity, f of x, let me show you some pictures, you guys. Here's some pictures, okay? Here's when it's odd. It's going to be looking like this, okay? And when your leading coefficient is positive, it starts down here and it goes, think of a straight line and a positive slope. A positive slope would go like this. It's going to go like this, where it starts down here and it goes up in that direction. Okay, so as x goes that way, f of x is going that way. So as x goes to negative infinity, f of x is going to negative infinity. As x goes to positive infinity, I'll use this one. As x goes that way, my graph f of x is shooting up that way. So as x goes to positive infinity, f of x is going to also positive infinity. Okay, remember if it's odd this time and it's negative, you're going to have graphs that look like that. Okay, so as x goes to the left, f of x is going up. So as x goes to negative infinity, f of x goes to positive infinity. And as x goes to the right, f of x goes down. And again, think of these guys like the slope of a line. A negative slope would go like this. Okay, now that's only when it's odd. When it's even, it's the touchdowns or upside down touchdowns, okay, depending on if it's positive or negative. So describe the end behavior. Okay, now check this out. Negative 2x to the fourth plus x minus 2. Okay, we'll make that equal y, you guys. Okay, make that equal f of x or equal y. Okay, notice this guy is even, that guy is negative. So as x goes to, it doesn't matter, positive or negative infinity, this is the upside down touchdown. It's going to be f of x always goes to negative infinity. Okay, how about this one? And I should have wrote f of x in there. F of x equals 6x to the fifth minus 3x cubed plus x minus plus 5. But all I'm concerned with is that's odd, that's positive, so it's going to be going up like this, you guys. So as x goes to negative infinity, f of x goes down to negative infinity. As x goes to positive infinity, f of x also goes to positive infinity. Okay, so graph each function using your graphing calculator and determine which intervals the graph is increasing or decreasing. Okay, so here's f of x equals 3 minus the quantity x minus 5 quantity squared. Plug that in your calculator. You should get a graph like that. Okay, now can you see this graph is increasing right here, and then at this x value right here, at this x value, it decreases. So f of x is increasing, and it looks like this scale is 1. So 1, 2, 3, 4, 5. So it increases when x is less than 5, and it starts decreasing when x goes greater than 5. Okay? So at 5, x equals 5 is called a critical point. That's when it changes from increasing to decreasing. Okay, what about this guy? Plug that in your calculator, and you should get a graph that looks like that. Okay, so over here, it's decreasing when x is less than negative 3, and it's increasing when x is greater than negative 3, so negative 3 is a critical point. Okay, let's do one more here. Okay, this guy right here, plug that in your calculator, you get a graph that looks like this. Okay, here it goes increasing right here, then it starts decreasing, then it starts increasing. Okay, so it's increasing when x is less than negative 2, and it's also increasing, oh wait. And it's also increasing when x is greater than 1, that's over here. And it's decreasing in between. It's decreasing in between these two intervals when x is between negative 2 and 1. So your critical points are x equals negative 2 or 1.